In this module, we will introduce partial molar quantities. How do state functions of a system change when we mix multiple liquid components together? For illustration, let's focus on the state function of volume. For each component in the mixture, we denote the amount of substance by Ni. The molar volume of each individual component I in its pure form is given by Vmi. If we were to calculate the total volume by multiplying the molar volume of each component with its respective amount and then summing everything together, the resulting volume would not match the actual volume of the mixture. So, what's the reason behind this discrepancy? The truth is, many physical properties of pure substances are not strictly additive upon mixing. When you mix substances, the resultant property of the mixture isn't merely the sum of the individual properties of the pure substances. To explain this, imagine two separate liquids. In their pure states, the molecules of each liquid are surrounded only by molecules of the same type. However, when mixed, the environment of each molecule changes due to the presence of different molecules from the other liquid. These intermolecular interactions between molecules of different types add complexity to the collective behavior of the mixture. To understand how properties change in a mixture, we introduce the concept of partial molar quantities. When considering an extensive property X for a mixed phase, such as volume, internal energy, enthalpy, entropy, or Gibbs energy, the total volume of X is not just a straightforward sum of the values for each pure component. Instead, we sum up the product of the amount of each component and its partial molar quantity, represented as X bar Mi. This partial molar quantity is not a characteristic of the pure substance, but rather represents how that component contributes to the total value of the property within the mixture. Each partial molar quantity is a property of the entire mixture and is influenced by all components. Mathematically, the partial molar quantity X bar Mi for a component I is the partial derivative of the total quantity X with respect to the amount of that component Ni at constant temperature, pressure, and the amount of all other components. Thus, it also indicates how a quantity changes due to a slight change in the amount of one component. Furthermore, the differential of the quantity X for the entire mixture at constant pressure and temperature can be expressed as the summation of products of partial molar quantities for all components and the differential of their respective amounts. This provides a precise way to describe how the overall property of a mixture changes due to small variations in its composition. Consider again an extensive property denoted as X. It is equal to the sum of the amount of each component multiplied by its partial molar quantity. The amount of each component Ni can be represented as a product of its mole fraction Xi and the total amount of substance in the mixed phase. The average molar value of X, represented as Xm, is the total value of X divided by the total amount of substance. It can be derived by multiplying the partial molar properties of each component by its respective mole fraction and then summing them up. This average molar value of X is an intensive quantity independent of the system size. The differential of the average molar value of Xm at constant pressure and temperature, dXm, is the sum of products of partial molar quantities for all components and the differential of their mole fractions. These equations indicate that partial molar quantities are not influenced by the absolute amount of each component in the mixed phase. Instead, they are defined by the relative composition of the mixture. In general, partial molar properties are functions of C plus 1 intensive state functions, temperature, pressure, and C minus 1 mole fractions. This is an illustration of the fact that the state of a mixed phase is defined only by intensive variables, including its relative composition.